Hi everyone. In this video, we are going to discuss about various guidelines associated with the mechanical translational system. We are going to see how to find a transfer function of the mechanical translational system. And also, we are going to see one problem on mechanical translational system. Here, mathematical modeling of a mechanical translational system guidelines we are going to discuss. So the step 1, we have to assign the displacements to each nodes. Here the nodes are nothing but masses. We have multiple masses in the system, so we'll be considering that mass as a node. And after that, for each mass, you have to draw a free body diagram. Then, step 3, you have to write the force balance equation. We are going to use a Newton's second law. Using that, we can write a force balance equation. Then we have to take a Laplace transform for those differential equations formed by force balance equation. And we have to rearrange the Laplace domain equations. Finally, we will get the transfer function. And these are the guidelines for modeling the mechanical rotational system. The same step what I have discussed in the previous slide. We have to assign the displacement. Here it is an angular displacement, theta 1, theta 2, theta 3, etc. For each node, the node is nothing but the moment of inertia, that is a mass. For each node, we have to write a torque balance equation, and before that you have to sketch the free body diagram. And by writing the torque balance equation, you will get a differential equation. For that differential equation, we have to take a Laplace transform. Then we have to rearrange those terms. We will get the required transfer function. So let us see a problem on mechanical translational system. This is the mechanical translational system given. You have to write the differential equations governing this mechanical system, and we have to find the transfer function. So here if you observe, this particular system has two masses. So we have two nodes, and here there is an applied force. Because of this applied force, this mass will move. That displacement is represented by x, and this mass will also move, whose displacement is represented as x1. Let's see how to get a differential equation and transfer function. So in this mechanical system, we have two nodes, one at M1, another one at M2. What we have to do, the first step, we have to draw the free body diagram for M1. So this is the free body diagram. You can see here M1 is a first mass. We are representing the free body diagram like this. For this particular mass, you have to consider all the elements which are connected with this mass. So you have M1, so it will oppose some force which is represented by F, M1. All the opposing forces are represented by inward arrows. All the applied forces I am going to represent using outward arrows. And this B1 is a dash part. One end is fixed with reference. So it is FB1. And we have this B and this K. So I am writing it as FB, FK as well as this particular K1, FK1. So totally we have 1, 2, 3, 4, 5 elements. So there will be a 5 opposing forces. So I am writing the opposing forces by means of the equation. Fm1 is m1 into d square x1 by dt square. Fb1, it is b1 into dx1 by dt. Fb is nothing but this b is connected with m1 and m2, between m1 and m2, so you will have displacement at both the ends. So it is, now we are considering the m1 as a reference, so it is x1 minus x. And this particular spring, it is attached with a reference, so it is Fk1 is nothing but k1 into x1, whereas this spring is available between these two masses, so we have a differential displacement, it is x1 minus x. By Newton's second law, we can write the sum of applied force is equal to sum of opposing force. For this particular mass, applied force is 0 because you don't find any f of t. So it is 0. So I am adding all opposing forces. You have to add Fm1, Fb1, Fb, Fk1 and Fk. This is what I have written here. This is the equation, differential equation governing that mechanical system. Now you have to take a Laplace transform for this equation. So m1 is a constant, d square. When you find d square, if you take a Laplace transform, it is s square. When you find d by dt, when you take a Laplace transform, it is s. If you take a Laplace transform of x1, it is x1 of s. This x1 is varying with respect to time. So it is x1 of s. b1 s into x1 of s. b into x1 of minus x of s. Because of this d by dt, you are finding s here. Then k1 x1 of s, k x1 of s minus x of s, which is equal to 0. From this, I am taking x1 of s outside and I am finding the x1 of s from this equation. So this is equation number 1. Now we have another mass, so we have to draw the free body diagram too. Can see here M2. If you see this particular M2, you have the components like B2, K and F. This is B. So totally we have 4 elements which are connected and we have an applied force. It is a pulling force. So it is represented by an outward direction. All the opposing forces are represented by an inward direction. So I am writing the opposing force equations, and by Newton's second law I can tell that applied force F of t is equal to opposing force. All these terms to be added. So I have added here, and we have to take the Laplace transform for this. Whenever you take a Laplace transform of x, it is x of s. Whenever you find d square, it is s square. Whenever you find d by dt, if you take a Laplace transform, it is s. So this is a Laplace transform of this particular differential equation. If you take a Laplace transform of f of t, it is nothing but f of s. Now, I am taking x of s outside from this equation, and you know that in the equation 1 we have computed x1 of s, that I am substituting in this place. So therefore x of s into this particular term we can take as such. X1 of s is nothing but x of s into bs plus k term will come. Here you will have bs plus k, so it becomes whole square. So now you have to rearrange this term to find the transfer function. What is a transfer function? We know that it is an output to the input. What is the output? It is a displacement. We are considering M2 whose displacement is x, and we know that we are applying an input as a force. So it is x of s by f of s. That's what I have computed. Just we have to rearrange the term such a way that you will get a transfer function. This is how you have to compute the transfer function of the given mechanical translational system. Thank you. These are the references.